Hello everyone, I'm Keisuke Sugura from K University. So today I'm going to present my work, an efficient accelerator for deep learning-based point cloud registration on FPGAs. So point cloud registration is a basis for many real-time robotic applications, and it tries to align two point clouds by estimating a 3D rigid transform. In this work, we develop a deep learning-based efficient and lightweight registration pipeline on FPGA SoCs to achieve better speed accuracy trade-off and enable fast registration on mobile robots. So many registration methods have been proposed over the past 30 years, and ICP is one of the most widely known methods. In ICP, we first find the correspondences between point clouds, and then we minimize the distances between corresponding point pairs to estimate a 3D rigid transform. So ICP is simple and easy to implement, but there are some weaknesses. So ICP requires the costly nearest neighbor search. So for every point in this red point cloud, we have to find its nearest neighbor in the right point cloud. So this leads to at least order n log n complexity. And ICP is prone to wrong correspondences. So deep learning-based approach is the current research trend. And many methods rely on the point correspondences, just like ICP. So these methods extract features for each point and find the correspondences by matching features, and uses SVD to obtain a 3D rigid transform. So these methods consider all the point pairs to make neural networks differentiable. So this means these methods require an order n squared time and space complexity, and the scalability is limited. So we focus on the correspondence-free and Lucas-Canaday-based approach called PointNetLK. PointNetLK first extracts the global features from point clouds using PointNet. So PointNet is a very famous neural network architecture for point cloud processing. Then PointNetLK iteratively aligns these PointNet features using Lucas-Canaday. PointNetLK has some benefits. So it requires only order n time and space complexity, and it is very suitable for parallel implementation, and it doesn't require any costly preprocessing like normal estimation. Our contribution is based on the PointNetLK, and we develop an efficient registration pipeline based on PointNetLK for resource-limited devices, especially FPGA SoCs. And we note this is the first work for deep learning-based registration on FPGAs. So we overview the PointNetLK. We would like to align a source point cloud to a template point cloud by estimating a 3D rigid transform from source to template. So in the initialization step, we compute a global feature of a template point cloud. Then we perturb the template and compute a feature for 6 times in total. So we now have 7 features in total. And from these features, we compute a Jacobian matrix J. And then we compute a pseudo-inverse of this Jacobian matrix K. So we have a template feature phi p and a Jacobian matrix K. And we proceed to the optimization step. So in the optimization step, we compute a feature of a source point cloud and compute a 3D rigid transform delta t. And we apply this transform to the source point cloud and go back to the first step. So we extract a feature from this transformed source point cloud. And this loop continues until convergence. And in PointNetLK, the PointNet feature extraction is a major bottleneck. So we can improve the entire performance by accelerating the PointNet inference. So we look at the architecture of PointNet. And PointNet consists of 5 MLPs and a max pooling layer. These 5 MLPs extract high-dimensional features for each point independently. Then this max pooling layer aggregates these pointwise features into a global feature. So PointNet is a very simple architecture and it doesn't have any random accesses to the input data. And it also doesn't require any preprocessing because PointNet takes the raw 3D point coordinates as input. And the number of parameters is fairly low. So PointNet is very suitable for hardware acceleration. So we look at the standard computation flow. So we take a point cloud of size n by 3 and compute pointwise features for all points at once using a set of matrix operations, producing a matrix of size n by 1024. And we apply a max pooling operation to this matrix to get a global feature. This standard approach, however, requires an order n memory space to store layer outputs. So this eats up the scarce on-chip memory and is not very resource efficient. So we take another approach to compute a global feature. So we consume each point one by one in a sequential manner and compute a feature and update a global feature by taking maximum. And we repeat this process for all points. So this modified approach requires a constant memory space to store layer outputs regardless of the number of input points. So this approach is much more memory efficient and scalable. So we perform the intra-layer optimization. So that is, we parallelize the computations in each layer using a standard optimization technique in high-level synthesis, which is loop unrolling and array partitioning. We also perform the inter-layer optimization. So we process multiple points in a pipeline fashion, and we can hide a large part of data transfer latency. We achieve this by a data flow optimization technique in HLS. And we look at the board level implementation for the length Z0104. And PointNet IP core and XIDMA controller are implemented on the PL part, and they interact with the PS part via two high-performance ports and AXI4 protocols. We set the operational frequency to 200 MHz, and we use Vitis HLS and Vivado 2020 for synthesis and place and route. So we used 32-bit fixed point format for both parameters and layer outputs. So as a baseline, we used a PyTorch implementation of PointNetLK and ICP, and we used a ModelNet 40 dataset, which contains around 5,000 CAD models of 40 object categories, like airplane, laptop. And we performed the registration as follows. So we sample some points from model vertices and normalize it to fit inside the unit cube. So we refer to this as a template point cloud. Then we rotate this template point cloud around a random axis by a fixed angle and translate it with a random 3D vector to create a source point cloud. So this we visualize the inputs to the registration in these figures. We first evaluate the registration accuracy in terms of the translational and rotational errors. So the blue line is a ICP, and it is clear that the PointNetLK achieves better accuracy than ICP, and FPGA-based PointNetLK maintains the same accuracy as the CPU counterpart. So we can say our PointNet IP core does not lead to accuracy loss. And we compare the PointNet inference time with the ARM Cortex CPU. And our FPGA-based implementation is much faster than CPU. So the FPGA naive implementation is 1.5 times slower than the CPU counterpart. And the intra-layer optimization speeds up the inference by 28 times, and inter-layer optimization speeds up the inference by 4.6 times. And the final FPGA design is 87 times faster than the CPU version. And compared to the Jetson Nano GPU, our FPGA-based PointNet IP core is consistently faster, as you can see in this graph. And we show the PointNet LK execution time in comparison with ICP. And the CPU version of PointNet LK is 3 times faster, and FPGA version is more than 100 times faster than ICP. So our PointNet IP core contributes to 35 times speedup, and we obtain a larger speedup with a larger number of input points. And compared to the Jetson Nano, our PointNet LK is consistently faster with our proposed FPGA acceleration. And we show the breakdown of the PointNet LK execution time in comparison with the CPU counterpart. So in the CPU counterpart, the PointNet feature extraction accounts for more than 90% of the entire execution time, but it is reduced to around 45% with our FPGA acceleration. So PointNet IP core effectively accelerates the bottleneck part. And we look at the FPGA resource utilization. And we note that all PointNet parameters and layer outputs can fit in block RAM slices, and we don't use the ultra RAM thanks to the constant space for layer outputs and lower number of PointNet parameters. So we finally compare the power consumption and energy efficiency. So for ZCU, we use INA219 power monitor. And for Jetson Nano devices, we use Tegra stats command. For PointNet LK registration, our FPGA-based registration pipeline achieved around 3.5 times better energy efficiency than CPU, and also 1.9 times better energy efficiency than Jetson Nano GPU. So our FPGA-based registration pipeline is faster and consumes less power than Jetson Nano GPU. So we demonstrate our FPGA-based registration pipeline using a Stafford-Bunny dataset. The left is a FPGA version, and right is a CPU counterpart. And as you can see, our FPGA-based registration pipeline is much faster than the CPU counterpart. So let me summarize the content in this presentation. So we presented our first work for deep learning-based registration on FPGA SoCs. And we focused on the correspondence-free approach called PointNetLK, which combines the PointNet feature extraction and Lucas-Canade-based feature alignment. Since the PointNet feature extraction is a major bottleneck, we developed a custom PointNet IP core. And we performed an intra and interlayer optimization. And also, we modified the computational flow in the PointNet. Our FPGA-based registration pipeline achieved 34 times faster registration than ARM CPU and more than 100 times faster registration than ICP. The energy efficiency was 3.5 times and 1.9 times better than ARM Cortex CPU and Jetson Nano GPU. So thank you for your listening.